What if I told you that the universe whispers its deepest secrets in patterns so profound, they repeat themselves from the smallest atom to the grandest galaxy? Picture this: a single snowflake, with its intricate, branching design, mirrors the sprawling structure of the universe itself. The same spirals that shape seashells and hurricanes also sculpt galaxies, as if nature is working from a hidden blueprint, stitching together the micro and macro worlds with threads of breathtaking symmetry. These aren't just coincidences, they're clues to something far more extraordinary, a cosmic code that binds everything, from the quantum realm to the edges of space. For centuries, scientists and philosophers have been captivated by these uncanny connections. Ancient cultures saw the divine in the harmony between the human body and the stars, while modern physicists uncover mathematical echoes between subatomic particles and celestial phenomena. Think about it: the way electrons orbit a nucleus isn't so different from planets circling a star. Even the vibrations of tiny strings in string theory resonate like cosmic symphonies, suggesting that the universe might be a fractal tapestry, repeating its patterns across unimaginable scales. It's as if the cosmos is playing a game of mirrors, reflecting itself in ways that defy our everyday understanding of size and distance. This video is your invitation to step through that looking glass. Together, we'll unravel 32 of the most astonishing parallels between the infinitesimal and the infinite connections so precise, they'll make you question whether small and large are even real distinctions or just illusions of perspective. We'll dive into groundbreaking science, from quantum mechanics to astrophysics, and even tap into wisdom traditions that sensed these links millennia before microscopes or telescopes existed. By the end, you won't just see the universe differently, you'll feel it, like a sudden realization that you've been part of a grand, interconnected dance all along. So, are you ready to uncover the hidden rhythms that pulse through every layer of reality? Let's begin. Take a close look at a sunflower's face. Those tightly packed seeds aren't scattered randomly. They spiral outward in opposing directions, following an exact mathematical rhythm called the Fibonacci sequence, where each number is the sum of the two before it. This same spiral appears in the curl of a nautilus shell, the arrangement of pine cones, even the branching of trees. But here's where it gets cosmic. Gaze at a spiral galaxy like the whirlpool, and you'll see those identical curves stretching across millions of light years. It's as if the universe sketched the same blueprint for a seashell and a star system, using the golden ratio as its compass. This divine proportion, approximately 1.618, shows up everywhere. Renaissance artists called it the secret formula of beauty, embedding it in masterpieces like the Mona Lisa. Architects used it to design the Parthenon, and composers wove it into symphonies. But nature got there first. When a plant grows, its leaves often emerge at golden ratio angles to maximize sunlight. Hurricanes churn with Fibonacci precision, and even the human ear echoes this spiral. The startling truth: the same math that organizes petals also sculpts galaxies. Astronomers find the golden ratio in the spin of black hole accretion disks and the distribution of matter in the cosmos, suggesting it's not just a pattern but a fundamental law. What does this mean? Some scientists propose the golden ratio is a shadow of deeper physics, a clue that the universe optimizes itself for efficiency, whether packing seeds or arranging stars. Others see it as evidence of a fractal universe, where similar structures repeat at every scale. Imagine a single equation describing everything from DNA coils to galactic arms. That's the tantalizing mystery of the golden ratio. It whispers that the very large and the very small might be far more connected than we ever dreamed. Now let's venture into the realm of quantum entanglement, a phenomenon so bizarre, even Einstein struggled to accept it. At the subatomic level, particles can become mysteriously linked, so that changing the state of one instantly affects its partner, no matter how far apart they are. This spooky action at a distance, as Einstein called it, defies our everyday intuition about how the universe should work. If two electrons are entangled, measuring the spin of one will immediately determine the spin of the other, even if they're light years apart. It's as if space and time don't exist for these particles, and they communicate through some hidden, instantaneous connection. But here's where the cosmic parallel emerges. Look up at the large-scale structure of the universe, and you'll find galaxies arranged in a vast, shimmering web, threads of dark matter stretching across unimaginable distances, with clusters of galaxies strung along them like pearls. These filaments aren't random, they're the scaffolding of the cosmos, guiding how matter clumps together over billions of years. And just like entangled particles, galaxies billions of light years apart seem to move in sync, as if tugged by some invisible force. Scientists call this phenomenon large-scale structure alignment, and it's eerily reminiscent of quantum entanglement on a cosmic scale. So what's really going on? Some theorists suggest that entanglement isn't confined to the quantum world. It might be woven into the fabric of space itself, operating at galactic and even universal scales. Others propose that dark matter, which makes up most of the universe's mass, could be entangled in ways we don't yet understand. Imagine if the entire cosmos is one vast, interconnected network, where galaxies influence each other not through gravity alone, but through something far more mysterious. This idea blurs the line between the infinitesimally small and the unimaginably large, hinting that the universe might be far more unified than we ever thought. The implications are staggering. If entanglement truly spans the cosmos, it could rewrite our understanding of space, time, and causality. Maybe the universe isn't a collection of separate objects, but a single, deeply connected system where every part resonates with every other part. From the dance of electrons to the grand sweep of galactic filaments, the same hidden threads might be tying it all together, an invisible hand guiding the universe toward harmony. Zoom in on a single neuron in the human brain, its delicate branches fanning outward like tree roots, then pull back to observe the cosmic web of galaxies, and you'll catch your breath at the similarity. Both systems stretch and split in ways that feel eerily familiar, as if painted by the same invisible hand. This isn't just visual poetry, it's fractal geometry in action, where patterns repeat themselves at every scale, from microscopic cells to galactic superclusters. The universe, it seems, has a favorite design trick. Take a simple rule, repeat it endlessly, and watch complexity bloom like a cosmic flower. Consider how a neuron's dendrites branch. Each split follows mathematical ratios seen in river deltas, lightning bolts, and even the air passages in your lungs. Now compare that to the way galaxies cluster along filaments of dark matter, threading the cosmos in a luminous web. Both structures emerge from the same principal efficiency. Neurons branch to maximize signal transmission. The cosmic web forms as gravity pulls matter along the most energy-efficient paths. It's as if nature has a playbook for building networks, whether they're made of star stuff or synapses. The magic of fractals lies in their simplicity. A single equation, repeated, can generate the jagged outline of a coastline or the swirling arms of a spiral galaxy. Mathematicians call this self-similarity, the idea that a small piece of the pattern contains the blueprint of the whole. Crack open a Romanesco broccoli and you'll see tiny florets mirroring the shape of the entire head. Gaze at satellite images of river networks, then at the veins in a leaf, and the resemblance is uncanny. Even the distribution of matter in the universe follows this fractal logic, with galaxy clusters nested within larger clusters, echoing the way cells organize into tissues and organs. What does this mean for our understanding of reality? Some scientists argue that fractals hint at a universe built on recursive rules, a kind of cosmic code where simple processes generate infinite variety. Others see them as evidence that certain shapes and structures are mathematically inevitable, emerging whenever energy flows through a system. Think of it like this: the universe might have a limited toolbox, reusing the same patterns because they simply work. Whether crafting a brain or a galaxy, nature returns to these fractal blueprints again and again, weaving order from chaos with breathtaking precision. The implications stretch beyond mere observation. If the brain's wiring mirrors the universe's structure, could there be a deeper link between consciousness and cosmos? Some theorists play with the idea that the universe itself might be a kind of neural network, with galaxies as nodes exchanging information. While this remains speculative, the fractal connection undeniably blurs the line between biology and astrophysics, suggesting that the same universal principles might govern growth, connection, and complexity at every scale. From the firing of a single neuron to the birth of a star cluster, the universe whispers its secrets in the language of repeating shapes, a fractal symphony playing on an infinite loop. At the heart of every atom lies a nucleus, a tiny, dense core holding nearly all its mass. Packed with protons and neutrons, it's a realm of unimaginable density, where nuclear forces battle to keep everything from flying apart. Now leap across the scales to a supermassive black hole lurking in the center of a galaxy. Though billions of times more massive, it shares that same mind-bending concentration of energy squeezed into a vanishingly small space. This isn't just coincidence, it's a cosmic echo, revealing how the universe repeats its most extreme phenomena at wildly different scales. Both black holes and atomic nuclei dominate their surroundings with forces that follow the same mathematical rule, the inverse square law. In simple terms, their pull weakens with distance squared, whether it's gravity from a black hole or the nuclear force binding protons and neutrons. Picture a magnet's hold on a paperclip strung up close, barely noticeable a few inches away. That's how these forces operate, creating zones of intense influence that drop off sharply. For nuclei, this keeps electrons in orbit. For black holes, it dictates the fate of entire stars. The eerie similarity suggests that when matter gets compressed to its limits, the universe defaults to the same playbook, regardless of size, but the parallels go deeper. Just as electrons whiz around a nucleus in specific energy levels, never in between matter spiraling into a black hole heats up and emits light in predictable, quantized patterns. Astronomers see this in the accretion disks of active galaxies, where superheated gas glows with telltale signatures. It's as if the cosmos is whispering that even in chaos, there's hidden order. Some physicists speculate that black holes might even resemble gigantic atoms, with event horizons acting like outer electron shells. While the scales are incomparable, the underlying principles feel oddly familiar. What does this duality teach us? For one, it hints that the universe might have a universal language for extreme conditions. Whether you're probing the quantum world or observing galactic centers, the same physics could be at work, just dialed to different magnitudes. Some theories even suggest that black holes could be cosmic particle accelerators, crushing matter down to fundamental building blocks, echoing how nuclear collisions in labs reveal the secrets of quarks. If true, studying one helps us understand the other, bridging the gap between the infinitesimal and the infinite. This connection also challenges our perception of scale. We think of atoms as unimaginably small and black holes as unfathomably large, but their shared behavior blurs that distinction. Perhaps size is just a matter of perspective, and the universe cares more about how energy is packed than how much space it occupies. From the crushing heart of a star to the fleeting collisions in a particle detector, extreme density might be the real universal currency, a thread stitching together the fabric of reality itself. Stretch your mind back to the universe's infancy, a searing, chaotic sea of energy just moments after the Big Bang. As it expanded and cooled, it left behind a ghostly afterglow we now call the cosmic microwave background, a faint whisper of radiation still detectable in every direction of space. But here's the astonishing part. When scientists mapped this ancient light with satellites like Planck, they discovered it wasn't perfectly smooth. Tiny fluctuations, ripples of hotter and cooler patches, were etched across the sky like cosmic fingerprints. These imperfections might seem random, but they're shockingly similar to the quantum foam theorized to bubble at the smallest scales of reality. It's as if the universe's largest relic and its smallest possible structures are mirroring each other across time and space. Quantum foam is one of the wildest ideas in physics. Imagine spacetime not as a smooth fabric, but as a churning, frothy ocean at scales trillions of times smaller than an atom. Particles and energy pop in and out of existence in a turbulent dance governed by Heisenberg's uncertainty principle. Now zoom out to those cosmic microwave background ripples. The patterns aren't just echoes of the Big Bang's violence, they're the seeds from which galaxies, stars, and planets eventually grew. Gravity amplified those tiny density variations, sculpting the universe's large-scale structure over billions of years. The jaw-dropping implication, the same quantum jitters that twist spacetime at microscopic levels, might have written their signature across the entire cosmos when it was smaller than a proton. This connection isn't just poetic. It's a potential clue to quantum gravity, the holy grail of modern physics. Some theories, like loop quantum gravity, suggest that spacetime's granular nature at tiny scales could have left imprints on the early universe's expansion. Think of it like blowing up a balloon with a slightly bumpy surface. Even as it inflates to enormous size, those initial imperfections stretch but never disappear. If true, the cosmic microwave background isn't just a relic. It's a magnifying glass revealing quantum mechanics operating at the birth of spacetime itself. The parallels grow even stranger when you consider inflation, the theory that the universe underwent a fleeting, hyper-speed expansion in its first fraction of a second. Quantum fluctuations during that explosive stretch would have been blown up to cosmic proportions, freezing into the density variations we see today. It's like tossing a handful of sand into a hurricane and watching the grains become mountain ranges. This interplay between quantum mechanics and cosmology suggests that the very large and the very small aren't just connected. They might be two sides of the same coin, with the universe's structure literally woven from quantum uncertainty. What does this mean for our understanding of reality? For one, it blurs the line between the quantum and cosmic realms in ways Einstein never imagined. The same physics governing subatomic particles could dictate the fate of galaxy clusters. Some researchers even speculate that spacetime's foamy texture might subtly alter light traveling across the universe, an effect we could one day detect with advanced telescopes. Whether these ideas hold up or not, the mere possibility reminds us that the universe loves repeating its patterns, from the tiniest quantum whirlpool to the vast afterglow of creation. The cosmic microwave background isn't just a snapshot of the past, it's a bridge between scales, whispering that the keys to the cosmos might lie in the quantum chaos from which everything emerged. Every atom of carbon in your body, every breath of oxygen you take, every strand of DNA coiled inside your cells, these weren't always here. They began their journey in the violent hearts of dying stars, where unimaginable pressures fused lighter elements into the building blocks of life itself. This is the staggering truth of stellar nucleosynthesis. The stars didn't just light up the cosmos, they became the cosmos, scattering their essence across space to eventually become part of you. Take carbon, life's backbone. It wasn't forged in the Big Bang, which only produced hydrogen, helium, and trace lithium. Instead, carbon was born in the fiery cores of red giant stars, where helium atoms crashed together under crushing gravity. That same carbon now forms the intricate lattice of your DNA, the sugar in your coffee, the pages of the book you're reading. Oxygen, another life-essential element, comes from even more dramatic stellar death supernovae so powerful, they briefly outshine entire galaxies. In their final moments, these exploding stars blast their chemical creations into the void, where they mix with interstellar clouds and condense into new stars, planets, and ultimately, living things. The parallels between stellar chemistry and biology are more than poetic. The nitrogen in your amino acids, the iron in your blood, even the calcium in your bones, all were minted in stellar furnaces. This means the very elements that allow your heart to beat and your brain to think were once part of celestial giants that lived and died billions of years before Earth existed. Astrophysicists call this cosmic recycling, but it's really a kind of alchemy on the grandest scale. The universe takes stardust and weaves it into planets, oceans, and eventually, creatures capable of gazing back at the stars and recognizing their own origins. Here's where it gets even more profound. The elements essential for life, carbon, oxygen, nitrogen, phosphorus, aren't just randomly abundant. They're precisely the ones stars produce most efficiently. Carbon's ability to form 4 bonds makes it the perfect scaffold for complex molecules, while oxygen's reactivity fuels the energy cycles of cells. It's as if the universe tilted the scales in favor of chemistry that could one day spark life. Some scientists argue this isn't coincidence but a consequence of fundamental physics. The same nuclear forces that govern stellar fusion also determine which atoms can become the bricks and mortar of biology. This connection reshapes how we see our place in the cosmos. You're not just on Earth, you are Earth, and Earth, in turn, is reconstituted stardust. Every time you inhale, you're drawing in oxygen atoms that might have once belonged to a star cluster in the Orion Arm. The gold in your jewelry likely came from colliding neutron stars, events so rare and cataclysmic, they're like cosmic treasure chests bursting open. Even the uranium-powering nuclear reactors was born in the explosions of massive stars, their dying breath seeding the galaxy with heavy elements. The implications stretch beyond mere chemistry. If life elsewhere exists, and the universe's relentless recycling suggests it's probable it too would be built from these stellar ingredients, alien DNA, if it exists, might rely on the same carbon chemistry, because no other element can match its versatility. This shared cosmic ancestry means that searching for life is, in a way, searching for pieces of ourselves scattered across the galaxy. We're not just observers of the universe, we're its awake, self-aware fragments, stardust that has learned to ponder its own origins. So the next time you look up at the night sky, remember, you're not just looking at the stars, you're looking at distant relatives, the ancient furnaces that forged the very stuff of your being. The boundary between astronomy and biology isn't just blurred, it's an illusion. From the ashes of dead stars to the pulse of living cells, the universe has been engaged in a single, unbroken act of creation, with you as its latest masterpiece. Imagine tracing the pathways of a single thought as it flickers through your brain. a spark leaping from neuron to neuron across a labyrinth of connections so dense it dwarfs the number of stars in our galaxy. Now pull back, way back, until galaxies themselves become pinpricks of light strung along filaments of dark matter, weaving a cosmic web that spans the observable universe. At first glance, these two networks couldn't seem more different, one inside your skull, the other stretching billions of light years, but peer closer and the similarities become uncanny. Both systems organize themselves into nodes and filaments, with clusters of neurons mirroring galaxy superclusters and synaptic gaps echoing the vast voids between galactic threads. It's as if the universe has a favorite way to build complex networks, whether it's wiring a mind or structuring spacetime itself. The magic lies in efficiency. Your brain's neural pathways constantly rewire to minimize energy use, prioritizing strong connections while pruning redundant ones, a process neuroscientists call synaptic pruning. Astonishingly, the cosmic web does something similar. Simulations of the universe's growth show matter flowing along the most economical gravitational paths, leaving empty voids and concentrating galaxies where filaments intersect. Both systems evolve toward optimal configurations, balancing connectivity with resource conservation. Think of it like city planning. Just as traffic naturally flows to the least congested routes, neurons and galaxies arrange themselves to avoid wasted effort. This shared principle suggests that whether you're mapping thought or matter, nature follows a universal playbook for building efficient networks, but the parallels go deeper than structure. Neurons communicate via electrical impulses, creating waves of synchronized activity that ripple through the brain patterns we detect as brain waves. On a cosmic scale, astronomers observe galaxies moving in coordinated flows, as if tugged by invisible currents in what's known as dark flow. While the mechanisms differ, neurotransmitters versus gravity, the emergent behavior feels eerily similar. Some theorists even speculate that galaxies might exchange information through gravitational waves, just as neurons relay signals across synapses. Could these large-scale motions be the universe's version of neural activity? The idea might sound like science fiction, but it raises a tantalizing question. If the brain thinks, and the cosmos resembles a brain, what might that imply about the nature of reality? This isn't just idle speculation. The holographic principle, a fringe but serious theory in physics, proposes that the universe might encode information on its boundaries, much like a brain stores memories in distributed patterns. Meanwhile, integrated information theory suggests consciousness arises from the way networks process information, whether those networks are made of neurons or, hypothetically, galaxies. While no one's claiming the universe is literally conscious, the structural echoes invite us to reconsider where complexity and connectivity might lead at vastly different scales. After all, if a 3-pound organ can generate subjective experience, what might 100 billion galaxies do, given the right configuration? The implications ripple outward. If neural and cosmic networks share fundamental organizing principles, studying one could unlock secrets of the other. Neuroscientists already use algorithms inspired by galaxy formation to model brain connectivity, while cosmologists borrow from neural network theory to simulate dark matter's behavior. This cross-pollination hints at something profound. The universe might not just contain complexity, it might embody it, repeating the same patterns from the micro to the macro, as if whispering that everything is part of a grand, interconnected whole. Whether you're contemplating a synapse or a supercluster, you're witnessing nature's relentless drive to weave order from chaos, building bridges between the seemingly disparate, and perhaps in the process, revealing that the line between the mind and the cosmos is far thinner than we ever dreamed. Ever notice how the flap of a butterfly's wings might theoretically set off a chain reaction leading to a hurricane weeks later? This iconic idea from chaos theory, known as the butterfly effect, reveals how minuscule, nearly imperceptible changes in initial conditions can spiral into dramatically different outcomes over time. Now, rewind the clock to the universe's first trillionth of a second, and you'll find a cosmic version of this phenomenon playing out on the grandest stage imaginable. During inflation, the universe's explosive expansion, quantum fluctuations tinier than a proton were stretched to astronomical scales, becoming the seeds for everything we see today: galaxies, stars, even the voids between them. What began as subatomic ripples in the fabric of spacetime ended up dictating the large-scale structure of the cosmos. The mechanism is startlingly similar to chaos theory's core principle: sensitivity to initial conditions. In weather systems, a slight shift in air pressure or temperature can alter storm trajectories weeks later. During cosmic inflation, quantum fluctuations, random, microscopic blips in energy, were magnified exponentially as space itself expanded faster than light. These tiny irregularities became gravitational fingerprints, areas where matter clustered slightly more densely. Over billions of years, gravity amplified these differences, pulling matter into the web of galaxies we observe now. Without those initial quantum jitters, the universe might have been a featureless void. Instead, they gave rise to the rich tapestry of cosmic structure, proving that the very small and the very large are locked in an intricate dance of cause and effect. Here's where it gets even wilder. The same mathematics used to model chaotic systems like pendulums or fluid dynamics also describes how inflation stretched quantum fluctuations. Both systems hinge on nonlinearity, where small inputs don't produce proportional outputs but instead trigger cascading, unpredictable transformations. A single quantum fluctuation might have determined whether a galaxy cluster formed here or there, just as a single butterfly's flight path might steer a storm toward one coastline instead of another. The universe, it seems, loves turning microscopic randomness into macroscopic order, whether it's shaping a hurricane or sculpting a supercluster, but there's a crucial difference. In chaos theory, outcomes are fundamentally unpredictable because we can never measure initial conditions with infinite precision. Cosmic inflation, however, had a built-in amplifier: the exponential stretching of spacetime itself. Quantum fluctuations didn't just propagate, they were frozen into the fabric of the universe, their patterns preserved in the cosmic microwave background like fossils. This means that while a butterfly's influence gets lost in the noise of Earth's atmosphere, quantum fluctuations left permanent scars on the cosmos. Astronomers can now map those scars, reconstructing the universe's quantum origins with telescopes. It's as if we've found the universe's butterfly, a trillionth of a second dulled speck of spacetime, and traced its wingspan across billions of light years. What does this cosmic butterfly effect teach us? For one, it blurs the line between quantum mechanics and relativity, two pillars of physics that rarely speak the same language. Inflation's ability to magnify quantum events into gravitational phenomena hints at a deeper unity, a theory of quantum gravity waiting to be discovered. It also reshapes how we think about randomness and destiny. The universe didn't unfold along a predetermined path. Its structure emerged from quantum dice rolls, frozen into permanence by inflation. Those rolls gave us a cosmos rich with galaxies, planets, and perhaps life itself. Had the quantum fluctuations been slightly different, we might not exist to ponder them. So the next time you hear about the butterfly effect, remember, the most dramatic example isn't on Earth, it's written across the night sky. From the quantum foam to the galactic web, the universe whispers that size is an illusion and that the smallest things often cast the longest shadows. Whether in the whirl of a storm or the birth of a galaxy, chaos and order are two sides of the same coin, spinning through the cosmos on the wings of chance. In a high-voltage lab, scientists create miniature bolts of twisting plasma ionized gas so hot, electrons tear free from their atoms. These glowing tendrils writhe and knot in chaotic dances, forming shapes that look eerily alive. Now point a telescope at the sun, and you'll witness the same serpentine structures, vast solar prominences, arcing millions of miles into space, or the twisted ropes of plasma in a nebula light years across. These aren't just visual coincidences, they're proof that electromagnetism sculpts the universe with the same brushstrokes, whether in a handheld experiment or a cosmic furnace. The secret lies in plasma's fourth state of matter, where atoms split into free electrons and ions, becoming conductive and responsive to magnetic fields. On Earth, lab plasmas twist into helical filaments because electric currents generate their own magnetic fields, which then channel the plasma into self-organizing strands. Out in space, the same physics unfolds on stupendous scales. Solar prominences are gripped by the sun's magnetic field, while interstellar plasma weaves itself into filaments light years long, guided by galactic magnetic forces. Even the colossal jets blasting from black holes' beams of plasma stretching thousands of light years follow these universal rules of electromagnetism. What's startling is how precisely small-scale experiments mimic cosmic phenomena. In labs, physicists use devices called plasma Z-pinch machines to simulate stellar processes. When they run high currents through plasma, it constricts into twisted columns, replicating the instability patterns seen in solar flares. These experiments reveal that the same math describes both a lab spark and a supernova's aftermath. The equations balancing magnetic pressure and plasma flow don't care about size. They apply equally to a tube glowing on a bench or a quasar's jet piercing intergalactic space. This scaling law has profound implications. It suggests electromagnetism might be the invisible architect shaping structures across the universe. Take the Birkeland currents, theorized by early 20th century scientist Christian Birkeland, rivers of plasma flowing along magnetic field lines. His lab work predicted the vast cosmic currents now observed snaking through galaxy clusters, fueling star formation, and even guiding the rotation of galaxies themselves. Modern simulations show these currents act like cosmic wiring, transferring energy across interstellar distances with eerie efficiency. The deeper you look, the more the patterns repeat. Plasma filaments in labs exhibit a property called self-similarity, where subsections of a filament resemble the whole structure, a hallmark of fractals. Zoom in on a nebula's tangled veins, and you'll find the same recursive complexity. Even the universe's largest known structures, like the Hercules Corona Borealis Great Wall, a filament of galaxies over 10 billion light-years long, echo these plasma dynamics, as if gravity and magnetism are collaborating on a canvas stretched across eternity. So why does this matter? For one, it means studying plasma in a lab isn't just about mastering fusion energy or advanced propulsion. It's a window into the universe's operating system. By understanding how filaments form, we decode the processes lighting up active galaxies or energizing stellar nurseries. It also hints at a universe far more interconnected than we imagined, where the same forces arranging charged particles in a vacuum chamber might also be spinning the webs of galaxies. From the smallest spark to the largest structures in existence, electromagnetism weaves a single, unbroken story, one where the universe's blueprints are written in the language of swirling plasma. Take a close look at the outer shell of a common cold virus under a microscope, and you'll spot something extraordinary, a near-perfect geometric shape with 20 triangular faces meeting at crisp edges. This isn't just artistic flair, it's an icosahedron, one of nature's most stable and efficient designs. Now, shift your gaze to the molecular realm, where 60 carbon atoms arrange themselves into a hollow sphere called a buckeball, sporting that same 20-sided symmetry. At first glance, viruses and carbon molecules seem worlds apart, yet they've both stumbled upon identical architectural blueprints. This isn't coincidence, it's a silent testament to how the universe converges on optimal solutions, whether building microscopic invaders or molecular marvels. The icosahedron's magic lies in its efficiency. With 20 faces, it encloses maximum volume using minimal material, a perfect strategy for viruses that need to pack genetic cargo tightly. But stability matters just as much as space. The triangles distribute stress evenly, making the structure resilient, critical for a virus surviving harsh environments. Buckeballs, or Buckminster fullerenes, owe their nickname to architect Buckminster Fuller's geodesic domes, which use similar geometry to create lightweight yet ultra-strong structures. Here, carbon atoms bond in pentagons and hexagons, forming a soccer ball-like cage that's incredibly tough yet flexible. Both viruses and buckeballs achieve something remarkable: strength through geometry, proving that shape can be as important as substance when it comes to durability. Dig deeper and the parallels grow even more intriguing. Viruses self-assemble their protein shells, with individual molecules snapping together like magnetic puzzle pieces, no external builder required. Buckeballs form spontaneously too, often in the fiery aftermath of dying stars or lab experiments mimicking space conditions. This self-organization hints at a universal rule. Under the right conditions, matter tends to arrange itself into energy-efficient forms. Whether in a test tube or a supernova's debris, the drive toward stability and symmetry appears to be written into the fabric of reality itself. What's truly mind-bending is how these structures bridge biology and chemistry. A virus's capsid is made of proteins, while a buckeball is pure carbon, yet both arrive at the same shape because the mathematics of efficiency transcend material differences. Physicists call this convergent evolution at the molecular level, a sign that certain geometries are simply inevitable when systems optimize for strength, space, or energy conservation. Even beyond Earth, astronomers detect buckeballs floating in interstellar clouds, suggesting these forms might be universal building blocks appearing wherever carbon and physical laws intersect. The implications ripple across science. Virologists study icosahedral symmetry to design better vaccines, while materials scientists mimic buckeballs to create ultra-strong nanomaterials. Some researchers even speculate that these geometric containers could have played a role in life's origins, protecting early genetic molecules in the chaotic primordial soup. Whether shaping microscopic life or interstellar chemistry, the universe keeps returning to these elegant designs, as if whispering a fundamental truth. From the tiniest virus to the farthest reaches of space, simplicity and efficiency reign supreme. So the next time you catch a cold or marvel at a geodesic dome, remember, you're witnessing the same cosmic craftsmanship that sculpts stars and molecules alike. The universe, it seems, has a favorite shape, and once you start looking for it, you'll find it everywhere. In the microscopic battles inside your body, the carbon stardust drifting between galaxies, and perhaps even in the hidden patterns of reality itself. Picture the moon orbiting Earth, its rocky surface subtly flexing under our planet's gravitational pull, a phenomenon we call tidal forces. These same invisible hands that sculpt ocean tides also stretch and squeeze celestial bodies, leaving them slightly egg-shaped. Now shrink that concept down to the atomic scale, where molecules' tiny constellations of electrons and nuclei face their own version of tidal distortion when subjected to powerful electric or magnetic fields. At first glance, a moon and a molecule seem unrelated, but the physics governing their deformation is eerily similar, revealing a hidden thread between the cosmic and the quantum. Take a water molecule drifting in space near a pulsar, a rapidly spinning neutron star with a magnetic field trillions of times stronger than Earth's. Just as Earth's gravity tugs the moon's near side more forcefully than its far side, the pulsar's field exerts unequal forces on the molecule's positively and negatively charged ends. This stretches its bonds, warping its shape in a microscopic echo of tidal locking. On Earth, chemists observe analogous effects in lab experiments with intense lasers, where electromagnetic waves distort electron clouds like an invisible hand kneading dough. Whether it's gravity bending spacetime or fields twisting molecular geometry, the universe treats deformation as a universal language. The parallels deepen when you examine the mathematics. Both gravitational and electromagnetic tidal forces follow an inverse cube law. Their strength diminishes with the cube of distance. This means a molecule near a black hole's event horizon and a moon orbiting a gas giant experience distortion governed by equations nearly identical in form. The difference lies in scale and mechanism. Gravity curves spacetime itself, while electromagnetism tugs on charged particles. Yet the outcome, stretching, compression, and energy dissipation, is strikingly alike. Even the cracks on Jupiter's moon Europa, caused by tidal flexing, resemble the way molecules under stress emit photons as they relax, shedding energy in rhythmic bursts. What makes this connection more than just a curious coincidence? For one, it underscores how fundamental forces, though distinct, can produce similar patterns across scales. Astronomers study tidal disruption events where stars are shredded by black holes to understand extreme gravity. Meanwhile, materials scientists harness molecular distortion to design flexible polymers or tunable superconductors. Both fields rely on the same principles of strain and resilience, just applied to vastly different realms. It's as if the universe whispers that whether you're engineering a spacecraft or a nanomachine, the rules of deformation remain universal. This mechanical kinship also hints at deeper symmetries in physics. Some unified theories suggest gravity and electromagnetism could be low-energy shadows of a single primordial force. While unproven, the way both forces distort matter offers tantalizing clues. Imagine a future where manipulating molecular tides could help simulate cosmic phenomena in labs, or where observing galactic collisions informs new quantum materials. From the warping of spacetime to the flexing of chemical bonds, the universe keeps reminding us that the macro and micro are far more connected than they appear. Two verses in the same cosmic song, sung in different octaves but harmonizing perfectly. Deep in the fabric of spacetime, there might be cracks, not the kind you can see, but defects left over from the universe's fiery birth, thinner than a proton yet stretching across billions of light years. These hypothetical cosmic strings are like scars on reality itself, unimaginably dense filaments of pure energy that could warp space around them, bending light and even time. Now shrink your perspective down to the quantum realm where superstrings, the tiny, vibrating loops of string theory, dance in dimensions beyond our perception. At first glance, these two ideas seem worlds apart, one describing cosmic scale wrinkles, the other the fundamental building blocks of matter. But the similarities are too striking to ignore. Both cosmic strings and superstrings are theorized to be one-dimensional, unimaginably dense objects that could hold the keys to unifying physics' greatest mysteries. Cosmic strings, if they exist, would be relics of symmetry breaking in the early universe. Think of them as cosmic fault lines where space-time itself didn't smooth out perfectly during rapid expansion. Their gravitational influence could explain strange phenomena like double images of distant galaxies or unexplained ripples in the cosmic microwave background. Superstrings, on the other hand, are the heart of string theory's bold proposition that all particles are just different vibrational modes of these tiny strings. What's mesmerizing is how both concepts, though operating at vastly different scales, share a mathematical elegance. The equations describing a cosmic string's space-time curvature bear a haunting resemblance to those modeling a superstring's vibrational energy. It's as if the universe enjoys recycling the same profound ideas, whether it's stitching the cosmos together or composing the symphony of quantum particles. The parallels don't stop there. Both types of strings could be bridges between quantum mechanics and gravity, the holy grail of modern physics. Cosmic strings might carry immense tension, behaving like cosmic rubber bands that could snap and release gravitational waves detectable across the universe. Superstrings, meanwhile, inherently weave gravity into quantum theory by proposing that the graviton, the hypothetical particle carrying gravitational force, is just another vibration of the string. Some theorists even speculate that cosmic strings could be macroscopic manifestations of superstrings, like echoes of the quantum realm writ large across the cosmos. Imagine if the universe's largest structures were, in some way, magnified reflections of its tiniest constituents, a fractal harmony linking the infinitesimal to the infinite. This connection isn't just theoretical eye candy. If astronomers ever detect evidence of cosmic strings, perhaps through their unique gravitational lensing signatures or bursts of high-energy radiation, it could indirectly support string theory, offering clues about the universe's fundamental fabric. Conversely, breakthroughs in particle accelerators or quantum gravity experiments might reveal superstring behavior that mirrors cosmic string dynamics. The interplay between these ideas suggests a universe far more interconnected than we've dared to imagine, where the same underlying principles govern everything from the quantum foam to the cosmic web. Of course, skepticism remains. Cosmic strings are still purely hypothetical, and string theory, while mathematically beautiful, lacks experimental confirmation. Yet the mere possibility that these two speculative ideas might be different expressions of the same deeper truth is tantalizing. Whether they're wrinkles in space-time or vibrating strands of energy, strings both cosmic and super hint at a reality where scale is an illusion, and the boundaries between the very small and the very large blur into insignificance. The universe, it seems, loves a good thread, weaving its grandest designs from the same timeless patterns, whether spanning the heavens or humming quietly in the heart of an atom. Dive into the ocean's midnight zone, where anglerfish dangle glowing lures from their heads, and jellyfish pulse with eerie blue light, a mesmerizing display of bioluminescence, nature's way of turning chemistry into illumination. Now leap across the cosmos to the edge of a supermassive black hole, where quasars blaze with the brightness of 1 trillion suns, their light fueled by matter spiraling into oblivion. At first glance, these phenomena couldn't seem more different, one born from delicate molecular reactions, the other from spacetime's most violent extremes. Yet both are masterclasses in energy conversion, proving that light, in all its forms, is the universe's favorite language for revealing hidden processes. Bioluminescence works like a microscopic firefly show. Creatures like dinner flagellates tiny plankton that set waves aglow, mix luciferin molecules with oxygen and the enzyme luciferase, triggering a reaction that releases energy as light without heat. This cold light is staggeringly efficient. Nearly 98% of the energy becomes visible photons, a feat human engineers still struggle to replicate. Quasars, by contrast, are anything but cold. As gas and dust plummet toward a black hole's event horizon, friction heats them to millions of degrees, accelerating particles to near light speeds. These charged particles then spiral along magnetic fields, emitting synchrotron radiation, light so intense it outshines entire galaxies. Different mechanisms, yes, but the same breathtaking outcome: darkness transformed into radiant spectacle. What's truly fascinating is how both systems optimize energy use. Bioluminescent organisms often pair their light-producing chemistry with reflective tissues or lenses to direct the glow, much like a flashlight's reflector. Quasars, too, channel their energy. Jets of plasma shoot from their poles, focused by the black hole's spin and magnetic fields into beams that can pierce intergalactic space. Evolution and astrophysics, operating at opposite ends of the scale spectrum, both arrive at precision engineering to maximize light's impact. Even the colors tell a story. Deep-sea creatures frequently emit blue light because it travels farthest in water, while quasars shine brightest in ultraviolet and X-rays, the wavelengths that dominate high-energy environments. This parallel isn't just poetic. It's a clue to how the universe recycles energy. The same laws of thermodynamics govern both scenarios, whether it's the breakdown of organic molecules or the shredding of atoms by gravitational tides. In the abyss, bioluminescence helps creatures hunt, communicate, or evade predators. In the cosmic abyss, quasars act as lighthouses, their light seeding galaxies with energy that might one day spark star formation. Both processes remind us that light is more than illumination. It's information, carrying tales of transformation from the depths of an ocean or the edge of a singularity. The implications stretch beyond mere observation. Scientists study bioluminescent chemistry to design greener lighting technologies, while astrophysicists decode quasar light to map the universe's structure. Some researchers even speculate that extremophiles near hydrothermal vents could hint at how life might arise near energy-rich cosmic events like quasars. It's a humbling thought. The same principles that light up a firefly's belly also power the universe's most luminous objects, stitching together life and cosmology in a single, shimmering thread. Whether in the blackness of the sea or the void of space, the message is clear: wherever energy flows, light follows, painting the darkness with the signature of creation itself. Every snowflake that drifts from the sky is a tiny masterpiece of geometry, no two alike, yet all sharing that iconic six-fold symmetry. This delicate artistry emerges as water molecules arrange themselves into ice crystals, guided by temperature and humidity in the cloud. But venture into the depths of space, where a teaspoon of matter weighs as much as a mountain, and you'll find an uncanny echo of this crystalline perfection. Neutron stars, the collapsed cores of dead stars, develop crusts so dense their atomic nuclei squeeze into orderly lattices, forming crystals of a scale and strangeness that dwarf even the most intricate snowflake. The symmetry of snowflakes stems from water's molecular architecture. Each H2O molecule bonds with four neighbors at precise angles, building hexagonal patterns that branch outward in fractal elegance. Neutron star crusts obey a different, yet strangely parallel logic. Here, gravity crushes matter so fiercely that electrons merge with protons, leaving a sea of neutrons packed tighter than atoms in a diamond. Under this unimaginable pressure, atomic nuclei, now just clumps of neutrons, arrange themselves into a crystalline lattice, a grid so robust it can support mountains on the star's surface, despite being 100 trillion times denser than steel. What's astonishing is how both systems, one born in Earth's gentle clouds, the other forged in supernova fire, arrive at ordered structures through extreme conditions. Snowflakes crystallized near freezing, where subtle changes in humidity sculpt their arms. Neutron star crystals form at millions of degrees, where the universe's strongest forces compress matter into submission. Yet both reveal nature's knack for finding symmetry in chaos, as if beauty is an inevitability wherever energy and matter intersect. The parallels go deeper than aesthetics. Snowflakes' branching patterns arise from diffusion, limited aggregation, a process where water vapor molecules follow random paths until they stick to a growing crystal's edges. Neutron star crusts evolve through a kind of cosmic version of this, nuclear statistical equilibrium, where particles jostle under extreme pressure until they settle into the lowest energy configuration. In both cases, randomness gives way to order as the system seeks stability. Even the flaws mirror each other. A snowflake's imperfections arise from dust grains or air currents, while neutron star crystals develop defects where the lattice strains under gravitational tides from a companion star. This cosmic craftsmanship has practical implications. Scientists study snowflake formation to improve climate models or design ice-resistant materials. Neutron star crystallography, meanwhile, could reveal secrets of quantum chromodynamics, how quarks and gluons behave under conditions impossible to replicate on Earth. Some theories even suggest these star crust crystals might vibrate like tuning forks, emitting gravitational waves we could one day detect. From forecasting weather to probing the universe's fundamental forces, the same principles of crystallization bridge disciplines light years apart. So the next time you catch a snowflake on your mitten, remember, you're holding a cousin to the universe's most exotic gems. Whether in the quiet drift of winter or the violent crush of a stellar corpse, nature returns again and again to the poetry of crystals, proof that order and beauty aren't accidents, but universal constants written into the fabric of reality itself. A leaf soaking up sunlight and a star blazing in the void might seem like opposites, one gentle and green, the other violent and incandescent. Yet both are cosmic alchemists, transforming light into life-sustaining energy through processes so similar in purpose. They reveal a universal truth. Whether on Earth or in the heavens, energy conversion is the heartbeat of existence. Photosynthesis and stellar fusion are nature's ultimate power plants, operating on scales trillions of times apart, but united by their role as engines of creation. Inside a plant cell, chlorophyll molecules act like microscopic antennas, tuned to capture photons from sunlight. When light strikes, it excites electrons, kicking off a chain reaction that splits water molecules and stitches carbon dioxide into sugars, the currency of life. This elegant dance converts solar energy into chemical bonds, fueling everything from towering redwoods to the algae in a pond. Meanwhile, in the core of a star like our Sun, hydrogen nuclei collide under crushing pressure and temperatures reaching 15 million degrees. These collisions fuse atoms into helium, releasing energy as photons that will spend thousands of years fighting their way to the surface before streaming across space. One process builds sugars, the other forges elements, but both are, at their essence, acts of light transmuted into something greater. The parallels extend beyond mere function. Both systems rely on precision-tuned structures to maximize efficiency. Chlorophyll's molecular arrangement allows plants to absorb specific wavelengths of light, mostly blue and red, while reflecting green, which is why leaves appear verdant to our eyes. Stars, too, have an optimal absorption spectrum. Their opacity dictates how photons escape, with heavier stars burning hotter and bluer, much like how shade-tolerant plants adapt to low light. Even the waste products mirror each other. Plants exhale oxygen as a byproduct of photosynthesis, a gas that later fuels fire and respiration. Stars, as they age, fuse heavier elements like carbon and oxygen, seeding the cosmos with the raw materials for planets and, ultimately, life. This isn't just poetic symmetry, it's a clue to energy's universal blueprints. Photosynthesis operates at roughly 95% quantum efficiency. Almost every photon absorbed triggers an electron transfer. Fusion in stars is less efficient by mass but unimaginably productive in scale, converting 4 million tons of matter into energy every second in our sun alone. Both processes abide by the same law. Energy cannot be created or destroyed, only transformed. A sunflower's growth and a supernova's blaze are chapters in the same story, where light bridges the living and the cosmic. What's truly humbling is how these processes interlock across time. The carbon in your body was forged in ancient stars, while the oxygen you breathe was likely spun off by cyanobacteria billions of years ago. The sunlight warming your skin, it began as fusion energy 8 minutes ago, completing a journey that echoes the way plants shuttle energy from chloroplast to root. This interdependence suggests that energy flows in a grand, unbroken circuit from star to leaf, from supernova to cell. The implications ripple outward. Scientists study photosynthesis to improve solar panels, mimicking nature's efficiency. Fusion researchers, meanwhile, chase the dream of stellar power on Earth, seeking clean energy from the same reactions that light the stars. Both pursuits remind us that whether we look to a leaf or a star, the answers to pressing challenges, sustainability, energy, even the origins of life, might lie in understanding how the universe naturally harnesses light. From the humblest blade of grass to the mightiest supergiant, the message is clear. Energy is the thread weaving the cosmos together, and light is its loom. Ever watched a sci-fi movie where heroes zip across the galaxy through a wormhole, a cosmic shortcut bending space and time? Now, zoom in trillions of times smaller, and you'll find particles pulling off their own version of this magic trick. Quantum tunneling lets electrons and other particles do the impossible, vanish on one side of an energy barrier and reappear on the other, as if they've teleported through solid walls. At first glance, tunneling seems worlds apart from the space-time warping tunnels of general relativity, but the parallels between them are too striking to ignore. Both phenomena whisper that the universe might be full of hidden doorways, where the rules of here and there aren't as rigid as they seem. Picture an electron trapped behind an energy barrier, like a ball rolling up a hill but lacking the speed to crest it. Classical physics says it's stuck forever, yet in the quantum realm, the electron has a chance to materialize on the other side, not by climbing over, but by appearing to dig straight through. This isn't science fiction. It's how solar panels convert sunlight into electricity and how radioactive atoms decay. The math behind tunneling reveals particles don't so much travel as they sample possible locations, exploiting the fuzzy probabilities of quantum mechanics to bypass obstacles entirely. Now compare that to a wormhole's throat, a hypothetical bridge where spacetime folds back on itself, turning a billion light-year journey into a stroll across a cosmic hallway. Both concepts defy classical intuition, suggesting reality has loopholes where distance and barriers become optional. The resemblance goes deeper than metaphor. Wormholes, as theorized by Einstein and Rosen, emerge from equations where spacetime curvature becomes so extreme it pinches into a tunnel. Quantum tunneling, meanwhile, arises from wave-particle duality, the idea that particles are also probability waves smeared across space. In both cases, the universe seems to permit shortcuts when conditions align. Even the limitations mirror each other. Wormholes likely require exotic matter with negative energy to stay open, just as tunneling probabilities drop exponentially with thicker or taller barriers. It's as if nature has a playbook for circumventing obstacles, whether they're energy hills in an atom or the vast gulfs between stars. What makes this connection more than just a fun thought experiment? For one, it hints that spacetime might share quantum mechanics' probabilistic weirdness. Some quantum gravity models suggest wormholes could be macroscale versions of quantum entanglement Einstein's spooky action at a distance, scaled up to warp spacetime itself. Others propose that every quantum tunneling event creates a fleeting, microscopic wormhole in the fabric of reality. While speculative, these ideas blur the line between the very small and the very large, implying that the universe's architecture might be far more interconnected than our classical senses perceive. Practical implications abound. Tunneling is already the workhorse of modern electronics, from flash memory to scanning tunneling microscopes that image atoms. If wormhole-like phenomena operate at quantum scales, could we one day harness them for communication or computation? Theorists have pondered whether traversable wormholes might exploit quantum coherence, the same delicate state that powers quantum computers. Meanwhile, experiments with tunneling particles are probing the limits of causality, testing if effects can precede causes in certain quantum regimes, a notion that wouldn't feel out of place in a wormhole's twisted timeline. This duality challenges our notions of impossibility. Particles that tunnel and spacetime that tunnels might simply be two expressions of a deeper truth, that barriers are illusions shaped by perspective. From an electron-hopping atoms in your phone's chip to a black hole's hypothetical backdoor, the universe keeps reminding us that solid and distant are concepts waiting to be rewritten. Whether through the quantum fog or the warps of relativity, reality seems obsessed with shortcuts, as if the cosmos itself is impatient, always seeking the fastest path from A to B, no matter how many dimensions it has to bend to get there. Beneath the ocean's sunlit surface, coral reefs pulse with life, a kaleidoscope of fish darting through labyrinthine structures built by tiny polyps over centuries. These underwater metropolises thrive on collaboration and competition, where every nook shelters creatures adapting to their niche. Now, lift your gaze to the cosmos, where galaxies huddle together in colossal clusters, bound by gravity's invisible threads. Though separated by scale, reefs and galactic clusters share an uncanny kinship. Both are bustling hubs where countless interactions birth staggering complexity, proving that the universe loves weaving intricate tapestries from simple, repeating stitches. Coral polyps, no larger than a grain of rice, secrete calcium carbonate to construct skeletons that grow into towering formations. Over millennia, these skeletons become the foundation for entire ecosystems, hosting everything from microscopic algae to apex predators like sharks. Similarly, galaxies within clusters, each home to billions of stars, drift and collide, their gravitational dances sculpting the cluster's shape and triggering bursts of star formation. In both cases, individual components, polyps or stars, follow basic rules, yet their collective behavior spawns systems of breathtaking diversity. A reef's health hinges on symbiosis, like the partnership between coral and photosynthetic algae. Galactic clusters, too, depend on interactions. Gas stripped from galaxies during collisions fuels new stellar nurseries, while dark matter's scaffold guides their motion. Parallels extend to their life cycles. Reefs face threats like bleaching when water temperatures rise, disrupting delicate balances. Galactic clusters also undergo stress when galaxies merge, tidal forces can shred stars or fling them into the void. Yet both systems demonstrate resilience. Coral polyps can repopulate damaged reefs if conditions stabilize, just as galaxy clusters redistribute gas and stars to form new structures over eons. Even their visual echoes are striking. Satellite images of the Great Barrier Reef's sinuous branches resemble computer simulations of the Virgo cluster's filamentary galaxy distribution, as if nature used the same brush for both canvases. What does this teach us? For one, it suggests that complexity isn't top-down but emerges from the bottom up, whether in biology or astrophysics. A single polyp or star might seem insignificant, but en masse, they create environments that shape evolution itself. On reefs, predator-prey dynamics drive species to adapt dazzling camouflage or toxins. In galaxy clusters, gravitational encounters fling stars into new orbits or even eject them entirely, a cosmic version of natural selection where only certain configurations survive. This bottom-up order might even hint at universal principles governing how complexity arises, from the quantum to the cosmic scale. The implications ripple beyond analogy. Marine biologists study reef resilience to understand ecosystem recovery, while cosmologists simulate galaxy clusters to decode the universe's large-scale structure. Both fields grapple with similar questions. How do interactions foster stability? What triggers collapse or renewal? By comparing these scales, we glimpse a deeper truth that the universe, for all its immensity, might operate on a handful of repeating algorithms, stitching together everything from coral colonies to galactic superclusters with the same elegant code. Whether in the shallows of a reef or the depths of space, complexity blooms from simplicity and connection fuels creation. Inside a high-security lab, physicists trigger a miniature star, a pulse of plasma hotter than the sun's core, wrangled into a magnetic cage for mere milliseconds. In that fleeting instant, something extraordinary happens. Magnetic field lines snap and realign, unleashing a burst of energy that makes the air crackle. This phenomenon, called magnetic reconnection, isn't just a lab curiosity, it's the same explosive process that powers solar flares, those eruptions on the sun's surface capable of disrupting satellites and painting the sky with auroras. What scientists are discovering is that the rules governing these fiery tangles of plasma don't care about size. Whether in a device the size of a school bus or a stellar inferno 100 times wider than Earth, the physics remains eerily identical, stitching together fusion research and astrophysics with threads of scaleless precision. The magic and chaos of magnetic reconnection lies in how it converts magnetic energy into heat and motion. Picture two rubber bands stretched side by side, storing tension. Now imagine they suddenly snap, cross, and fuse into a new configuration, releasing their pent-up energy in a whip-crack instant. That's essentially what happens when the sun's magnetic fields tangle and reconnect, hurling charged particles outward at nearly the speed of light. In labs like Princeton's magnetic reconnection experiment, physicists recreate these conditions by smashing plasma jets together, watching as the resulting energy release mirrors solar flare data down to the mathematical signatures. The same equations that describe a flare's X-ray spikes also predict the lab plasma's behavior, proving nature's laws don't discriminate between a star and a stainless steel chamber. This scalability isn't just academic, it's revolutionizing both energy science and space weather forecasting. Fusion reactors like tokamaks battle magnetic reconnection as an enemy, since it disrupts plasma confinement and cools the reaction. But by studying how flares harness reconnection to accelerate particles, engineers are designing better magnetic shields to stabilize fusion. Meanwhile, solar physicists use lab data to predict when a reconnection event on the sun might send a geomagnetic storm our way. It's a rare feedback loop where studying the cosmos helps tame plasma on Earth, and taming plasma unveils the cosmos's secrets. The implications stretch beyond our solar system. Astronomers spot reconnection signatures in the magnetospheres of Jupiter, in the jets of distant pulsars, even in the accretion disks of black holes. Each observation reinforces the idea that plasma, under the right conditions, behaves like a cosmic liquid with universal grammar, a language where magnetic fields are the syntax and reconnection is the exclamation mark. From the smallest lab spark to the largest stellar eruption, the universe keeps reminding us scale is an illusion and energy dances to the same tune everywhere. What's truly humbling is how this connection defies intuition. We expect the vastness of space to operate by different rules than our pocket-sized experiments. Yet here, in the violent snap of a magnetic field line, the universe whispers its unity, a reminder that the same forces shaping the stars are at work in our quest for clean energy, binding human ingenuity to the cosmic drama in ways we're only beginning to grasp. Watching a murmuration of starlings at dusk is like witnessing magic thousands of birds weaving through the sky as if guided by an invisible hand, twisting and turning in perfect synchrony without collision. Each bird reacts to its neighbors in real time, creating rippling waves of motion that seem to defy physics. Now, switch to a supercomputer simulation of dark matter, where countless particles move under gravity's pull, forming vast, shimmering halos around galaxies. At first glance, a living flock and a cloud of invisible matter couldn't seem more different. But the patterns they trace, the way individual elements create collective order, are nearly identical, revealing a hidden thread between biology and cosmology. The secret lies in emergent behavior. Starlings don't follow a leader or a preordained script. Instead, each bird obeys three simple rules: steer toward neighbors to stay cohesive, avoid collisions by maintaining space, and align with the group's direction. These local interactions generate global complexity, transforming chaos into choreography. Dark matter behaves similarly. While individual particles feel only gravity, their collective dance produces structured halos diffuse, spherical clouds that envelop galaxies. Supercomputer models show dark matter particles flocking along gravitational gradients, clustering where density is highest, just as starlings gather where the group's momentum flows. The result, both systems self-organize into dynamic, ever-shaping networks, proving that complexity can arise from simplicity when enough actors follow the same basic playbook. Parallels go deeper than visual poetry. Mathematically, the movement of bird flocks can be modeled using active matter physics, a framework describing systems where individual units expend energy to move like birds flapping wings. Dark matter halos, though governed by passive gravity, exhibit strikingly similar statistical patterns in their velocity distributions. Both systems settle into states of balanced tension. Birds trade off between cohesion and avoiding crashes, while dark matter particles orbit just fast enough to resist collapsing inward. This equilibrium creates stable yet fluid structures, whether a murmuration's fleeting shapes or a halo's billion-year embrace of a galaxy. What makes this connection more than a curious coincidence? For one, it suggests that certain organizational principles might be universal, transcending the boundaries between life and non-life. Researchers studying swarm robotics, for instance, borrow flocking algorithms to program drones to navigate autonomously. Cosmologists, meanwhile, use modified versions of these algorithms to simulate how dark matter filaments weave the cosmic web. The overlap hints that nature has a limited toolkit for building order, whether she's sculpting a starling's flight path or the scaffolding of the universe. This kinship also challenges our definitions of intelligence. A flock has no central brain, yet its collective decisions, like evading a predator, appear almost strategic. Dark matter halos, mindless as they are, adapt their shapes to the gravitational pull of neighboring galaxies, like a murmuration adjusting to wind currents. Both systems achieve sophistication without sentience, raising profound questions. Could intelligence be less about individual cognition and more about the emergent genius of interconnected parts? From neurons firing in a brain to stars tracing orbits in a halo, complexity thrives on simple rules and countless repetitions. The implications stretch beyond theory. By studying starling flocks, biologists gain insights into how decentralized systems, from immune cells to traffic flows, can achieve harmony without a conductor. Astronomers, conversely, refine dark matter models by testing how slight tweaks to interaction rules alter large-scale structure. This cross-pollination of ideas underscores a humbling truth. The universe adores patterns, reusing them in contexts as disparate as a sunset's avian ballet and the invisible architecture of the cosmos. Whether in the flutter of wings or the drift of particles, the message is the same: connection breeds complexity, and simplicity hides in the heart of the sublime. Sprinkle sand onto a metal plate, set it vibrating with sound waves, and watch as the grains leap into intricate geometric patterns, circles, stars, and mandala-like shapes that shift with each new frequency. This mesmerizing phenomenon, called cymatics, reveals how vibrations sculpt matter into order. Now, zoom out to the scale of our solar system, where planets trace elliptical orbits around the Sun, their paths governed by gravity's invisible pull. At first glance, a humming metal plate and a celestial dance seem unrelated, but the patterns they produce, those precise harmonic arrangements, are nearly identical, hinting that waves, whether acoustic or gravitational, might be the universe's favorite architect. The sand on a vibrating plate doesn't move randomly. It collects along nodal lines, areas where the plate's motion cancels out, leaving the grains undisturbed. These lines form symmetrical designs that mirror the standing waves creating them. A low frequency might generate concentric circles, while higher pitches produce intricate radial spokes. Astonishingly, when astronomers model the gravitational resonances between planets and their stars, they find similar harmonic structures. Jupiter's moons, for example, orbit in ratios that echo musical intervals, their gravitational pulls creating stable, repeating patterns just like the sand's nodal line. It's as if the solar system is a grand cymatic experiment, with gravity playing the role of sound. This parallel isn't just visual poetry, it's rooted in the mathematics of resonance. Every vibrating system, from a guitar string to a galaxy, has natural frequencies where energy builds constructively. In cymatics, these frequencies organize chaos into geometry. In space, they create orbital resonances, where planets or moons lock into stable, repeating rhythms. Saturn's rings, with their gaps and braided bands, are a textbook example. The gravity of nearby moons excites resonant frequencies that sweep some particles away while herding others into intricate formations. The same physics that arranges sand on a plate also sculpts the architecture of planetary systems. Dive deeper, and the connections grow even more profound. Cymatic patterns often resemble molecular structures or cellular membranes, suggesting vibration might underpin biology's blueprints. Meanwhile, astrophysicists detect resonant frequencies in the distribution of galaxies, as if the cosmos itself is ringing from ancient gravitational waves. Some theorists even speculate that dark matter, the invisible scaffold of the universe, could be shaped by standing waves on a galactic scale, with dense regions acting like nodal lines where matter clusters. Whether in a lab or the void of space, waves seem to whisper the same message. Structure emerges from rhythm. What does this mean for our understanding of reality? For one, it blurs the line between sound and gravity, two forces we typically consider separate. Both are vibrations propagating through a medium, air for sound, space-time for gravity, and both can impose order on chaos when tuned to the right frequency. This hints at a deeper, vibrational layer of reality where form follows frequency. Ancient cultures intuited this connection, linking musical harmony to celestial motion in concepts like the music of the spheres. Modern science now reveals they weren't entirely metaphorical. The implications ripple across disciplines. Architects use cymatics to design concert halls with perfect acoustics, while astronomers apply resonance theory to predict undiscovered exoplanets. Artists collaborate with physicists to sonify cosmic data, translating planetary orbits into audible tones. These experiments remind us that the universe might be less like a machine and more like a symphony, with waves as its fundamental notation. From the hum of a vibrating plate to the silent thrum of orbiting worlds, patterns repeat across scales, singing the same silent song, a testament to the vibrational threads weaving the cosmos together. In the dense jungles where chimpanzees forge alliances and jostle for dominance, an invisible pattern emerges, one that mirrors the sprawling megastructures of the cosmos. Primate societies, with their alpha leaders, shifting coalitions, and intricate grooming networks, aren't just chaotic social experiments. They follow a precise mathematical rhythm called a power law distribution, where a few individuals hold disproportionate influence while the majority occupy lower ranks. Now peer through a telescope at the universe's largest galactic superclusters, colossal gatherings of thousands of galaxies bound by gravity, and you'll find the same statistical signature etched across the cosmos. The universe, it seems, adores this asymmetry, whether organizing apes or galaxies, as if whispering that hierarchy isn't just a human construct but a fundamental law of complex systems. Power laws reveal themselves in striking ways. In a chimpanzee troop, the alpha male might control access to food or mates, while lower-ranking members form alliances to climb the ladder. Plot these relationships on a graph, and you'll see a curve where a handful of high-status individuals dominate, followed by a long tail of lesser influence. This same curve describes how galaxies clump together. A few massive superclusters, like the Laniakea supercluster housing our Milky Way, anchor vast filaments of matter, while smaller galaxy groups scatter like afterthoughts. The math governing a chimp's social rise and a galaxy's gravitational pull is eerily identical. Both systems favor the rich getting richer, where early advantages snowball into dominance. The mechanisms behind these parallels are where things get fascinating. In primate groups, social capital compounds through reciprocity and intimidation. A chimp that shares food might gain allies, while one that wins fights commands fear. Galaxies, in their own way, play a similar game. Larger galaxies grow even more massive by cannibalizing smaller neighbors through gravitational attraction, their sheer bulk warping spacetime to pull in more matter. Both systems operate on feedback loops. Success begets more success, whether through social grooming or cosmic mergers. Even the outliers align. Renegade chimps that buck the hierarchy resemble rogue galaxies ejected from clusters during violent collisions, both defying the norm yet still bound by the system's overarching rules. This isn't just a quirky coincidence. Power laws emerge in everything from earthquake magnitudes to internet traffic, suggesting they're a universal strategy for managing complexity. In primate societies, hierarchies reduce conflict by clarifying who gets what. For galaxies, clustering optimizes gravitational stability, preventing chaotic scatter. Both systems arrive at similar solutions because complexity, whether social or astrophysical, demands efficient organization. The universe, it seems, has a favorite algorithm for building order from chaos, and it's one that rewards aggregation and centralization, whether you're a bonobo or a quasar. What's truly humbling is how this connection bridges biology and cosmology. Primatologists use network theory to predict how alliances might shift after a power struggle, while astrophysicists apply similar models to simulate how galaxy clusters merge over billions of years. The tools are interchangeable because the patterns are universal. Some theorists even speculate that dark matter, the invisible glue holding galaxies together, might follow its own version of social hierarchy, with denser regions exerting disproportionate pull on their surroundings. The implications ripple beyond academia. Understanding power laws could help us design better cities where resources flow like social favors in a chimp troop, or more resilient infrastructure modeled after the cosmic web's distributed strength. It also challenges our notion of randomness. The universe isn't just tossing dice. It's running a deeply interconnected network where local interactions, whether grooming or gravity, create global order. From the jungles of Tanzania to the voids between superclusters, the message is clear. The cosmos speaks in power laws, and we're just beginning to decode its grammar. Spin a child's top on a table and watch as it pirouettes with unwavering stability, a tiny demonstration of angular momentum in action. Now, scale that image up by a factor of billions, and you'll find the same principle governing the whirling dance of galaxies. But here's where it gets mind-bending. This cosmic choreography isn't just a macroscopic phenomenon. Zoom into the quantum realm, and you'll discover subatomic particles like electrons and quarks also spinning, their intrinsic angular momentum as fundamental to their identity as their mass or charge. From the tiniest building blocks of matter to the grandest structures in the universe, spin isn't just a property, it's a universal language of motion, written into the fabric of reality at every scale. At the quantum level, spin defies everyday intuition. Particles don't literally rotate like miniature planets. Their spin is an intrinsic quality, a form of angular momentum baked into their existence at birth. Electrons, for instance, are always spinning at the same fixed rate, as if the universe stamped them with an unchangeable cosmic barcode. This quantum spin isn't just a curiosity, it's the reason magnetism exists, the secret behind MRI machines, and the foundation of quantum computing. Yet for all its strangeness, this microscopic spin shares a profound kinship with the majestic rotations of galaxies, which twirl like slow-motion tops under gravity's guidance. Both systems owe their motion to primordial torques, twists imparted during their formation that set them spinning and never stopped. The echoes between these scales grow even louder when you examine how spin shapes structure. In galaxies, angular momentum dictates their very form. A spiral galaxy's graceful arms are cosmic whirlpools, where rotation fights gravity's collapse, creating a delicate balance that preserves its shape for billions of years. Similarly, an electron's spin determines how it interacts with other particles, shaping the architecture of atoms and the chemistry of life itself. Without spin, electrons would collapse into atomic nuclei, and galaxies would crumple into formless blobs. This conserved motion, whether in a particle or a galaxy, acts as a cosmic stabilizer, a hidden hand maintaining order across the universe's hierarchy. What's truly astonishing is how both systems inherit their spin from chaos. Galaxies rotate because the collapsing gas clouds that birthed them were nudged by the gravitational tugs of neighboring matter, a tiny initial push amplified by conservation of angular momentum as the cloud contracted. Quantum particles, too, acquired their spin during the universe's fiery infancy, when symmetry-breaking events in the early cosmos locked in their fundamental properties. Both processes reveal a deeper truth. Rotation isn't an afterthought but a relic of creation, a fingerprint of the universe's turbulent beginnings preserved across time and scale. This connection isn't just poetic, it's a potential window into unifying physics. The same equations describing angular momentum in classical mechanics appear in quantum field theory, hinting at a shared mathematical backbone. Some theorists even speculate that galactic spin could be influenced by quantum-scale phenomena, like the collective alignment of primordial particle spins during cosmic inflation. While still speculative, the idea that quantum spins might have seeded the large-scale structure of the universe is a tantalizing bridge between the infinitesimal and the infinite. So the next time you see a spiral galaxy's portrait or ponder the spin of an electron, remember, you're witnessing the same cosmic principle at work, from the particles in your fingertips to the galaxies spinning in the void. The universe, it seems, never stops turning, and in that endless rotation, it whispers a secret of unity, written in the language of motion itself. Beneath the forest floor lies a bustling, hidden metropolis, threads of fungal mycelium weaving through the soil in intricate, branching patterns, shuttling nutrients between trees with astonishing precision. These vast underground networks, often called the Wood Wide Web, form symbiotic relationships with plant roots, trading minerals for sugars in a silent economy that sustains entire ecosystems. Now shift your gaze to the cosmos, where another invisible web stretches across the void. Dark matter, the unseen scaffold guiding galaxies into clusters and filaments. Though separated by scale, mycelium and dark matter share an eerie resemblance. Both are invisible architects shaping the visible world, proof that the most vital infrastructures often hide in plain sight. Mycelium operates like nature's internet, with fungal hyphae acting as living cables that transmit not just nutrients but also chemical warnings alerting trees to pests or drought. The largest known fungal network, a honey mushroom in Oregon's Blue Mountains, sprawls across 2,400 acres, making it one of Earth's biggest organisms. Dark matter's cosmic web mirrors this on a galactic scale. Its filaments, traced by supercomputer simulations, funnel ordinary matter into dense knots where galaxies form, while leaving vast voids between them. Just as mycelium's threads determine where seedlings thrive, dark matter's gravitational tug decides where stars will ignite. Both systems are invisible yet indispensable, their presence revealed only by their effects on the world we can see, trees flourishing in a fungal hub, galaxies spinning faster than visible matter alone should allow. The parallels go deeper than function. Both networks exhibit fractal-like branching, optimizing resource distribution across three-dimensional space. Mycelium grows by following nutrient gradients, extending tendrils where sustenance is richest. Dark matter, too, clusters along density gradients, its web thickening where gravity pools matter most intensely. Even their roles in resilience echo each other. Forests connected by mycelium recover faster from disturbances, while galaxies embedded in dark matter halos resist tearing apart during cosmic collisions. It's as if evolution and cosmology arrived at the same solution: efficient, decentralized networks to solve the universal challenge of sustaining complexity across vast distances. What makes this connection more than poetic metaphor? For one, it challenges our bias toward visible structures. We're conditioned to equate importance with what we can observe, yet these hidden frameworks suggest the real action happens behind the scenes. Ecologists once saw trees as solitary competitors. Now we know they're nodes in a fungal network, cooperating as much as competing. Similarly, astronomers once assumed galaxies floated in isolation until dark matter's gravitational fingerprints revealed a connected cosmos. Both discoveries force us to rethink independence as an illusion. Everything, from a Douglas fir to the Milky Way, is enmeshed in a web of invisible relationships. The implications ripple across disciplines. Researchers modeling dark matter's structure borrow algorithms from mycology to simulate filament growth. Conversely, biologists study cosmic web simulations to hypothesize how fungal networks might adapt to environmental stress. This cross-pollination of ideas hints at a deeper truth. Whether navigating soil or spacetime, nature favors networks that balance efficiency with redundancy. Mycelium's redundant pathways ensure survival if one thread fails, just as dark matter's multiple filaments allow galaxies to migrate when clusters collide. Perhaps most tantalizing is the philosophical thread linking these systems. Both raise existential questions about what it means to be alive. Mycelium blurs the line between organism and infrastructure, while dark matter defies categorization as anything but gravitational influence. Yet without them, forests would starve and galaxies would fly apart. They remind us that reality's most profound layers often elude our senses, waiting to be uncovered by those who dare to look beyond the visible. From the soil's whispering threads to the cosmos' silent scaffolding, the universe keeps whispering. Connection is the rule, not the exception, and the bonds that matter most are sometimes the ones we cannot see. Crack open a diamond with a hammer, an act bordering on sacrilege, and you'll expose its hidden architecture, a pristine lattice of carbon atoms stacked in perfect repeating cubes, each bond precise as a master jeweler's setting. But look closer and you'll notice something unexpected. The beauty of this crystal isn't just in its atoms, it's in the empty spaces between them, the geometric voids where nothingness becomes part of the design. Now leap across the cosmos to the Sloan Great Wall, one of the universe's largest known structures, where galaxies clump into sheets and filaments stretching over 1 billion light-years. Between these shimmering walls lie cavernous voids so vast, they could swallow thousands of Milky Ways without a trace. At first glance, a diamond's atomic gaps and the cosmic voids seem unrelated until you realize both are the silent sculptors of their realms, proving that emptiness isn't passive absence but an active force shaping everything we see. Crystallographers call these empty zones interstitial sites, the gaps where foreign atoms sometimes nestle, or where light bounces to give gems their sparkle. Remove them and crystals lose their strength and symmetry, the lattice collapses. Cosmic voids play an equally vital role. Without these expansive deserts, galaxies would crowd together like commuters in a subway car, their gravity tangling into chaos. Instead, voids act as gravitational buffers, their emptiness allowing galaxy filaments to stretch and breathe, much like the gaps in a diamond's lattice prevent atoms from crushing one another. Both systems rely on negative space to maintain order, a hidden blueprint where what's not there matters as much as what is. The geometry of these voids is where the parallels crescendo. In crystals, interstitial sites often form tetrahedrons or octahedrons, clean, angular gaps dictated by atomic packing. Cosmic voids, too, exhibit geometric regularity. Simulations of the universe's large-scale structure reveal that voids aren't random bubbles but polyhedral cells with flat facets, where galaxy walls intersect at precise angles. This isn't accidental. Just as atoms arrange themselves to minimize energy, galaxies distribute along gravitational troughs, leaving behind voids that approximate the universe's most efficient packing solution. Nature, it seems, adores efficiency, whether she's arranging atoms or galaxies. Dive deeper, and the functional echoes grow louder. In materials science, doping a crystal, intentionally adding atoms to its voids, can transform insulators into superconductors or turn glass into vibrant stained windows. Cosmic voids, too, aren't entirely empty. They're sparsely populated with void galaxies, rare loners that evolve differently than their crowded counterparts, much like atoms in a crystal's gaps behave unlike those in the main lattice. Some astronomers even speculate that dark energy, the mysterious force accelerating the universe's expansion, might exert its pull more strongly in these voids where gravity's grip is weakest. If true, voids could be cosmic laboratories for physics we've yet to fathom, just as crystal gaps host exotic quantum states unseen in bulk matter. This interplay of presence and absence reshapes how we perceive structure. A diamond's brilliance depends on light interacting with its voids as much as its atoms. Similarly, the universe's most stunning features, galaxy clusters, supernova nurseries, exist because voids carved the stage for them to shine. Remove the emptiness and both systems collapse into formless blobs. The lesson: wholeness requires hollows. Perfection hinges on pockets of nothing. From the quantum to the cosmic, the universe whispers that voids aren't flaws but features the silent partners in an endless dance between matter and space, each giving the other meaning. So the next time you admire a gemstone's glitter or a telescopic image of the cosmic web, remember, you're witnessing the same universal principle at work. Emptiness isn't just tolerated, it's engineered with mathematical precision into the fabric of reality. Whether in the heart of a crystal or the depths of intergalactic space, absence shapes existence, proving that sometimes nothing is everything. Consider the human brain for a moment, a 3-pound universe of its own, where 86 billion neurons fire in intricate patterns, weaving thoughts, memories, and dreams. Each second, your brain processes more information than all the libraries on Earth combined. Now, shift your gaze to the cosmos, where black holes swallow stars and quantum particles flicker in and out of existence. At first glance, these realms seem unrelated, but cutting-edge theories are revealing a startling possibility. The way your brain processes information might mirror how the universe itself manages entropy, the slow unraveling of order into chaos. This isn't just philosophy, it's a radical reimagining of reality where consciousness and cosmology could be two sides of the same cosmic coin. At the heart of this idea lies information theory, the science of how data is stored, transmitted, and transformed. Your brain's neural networks encode memories by strengthening synaptic connections, much like a computer writes ones and zeros to a hard drive. Meanwhile, the universe appears to operate on similar principles. Black holes, for instance, don't just trap matter, they compress information to its absolute limit, with their event horizons acting like cosmic hard drives. The holographic principle, a fringe but serious theory in physics, takes this further, suggesting the entire universe might be a projection of information stored on its boundary, like a 3D movie encoded on a 2D surface. If true, your thoughts could be part of a vast computational process, with neurons firing in harmony with the universe's own data streams. The parallels grow even stranger when you examine entropy, the measure of disorder in a system. In your brain, entropy increases as neurons fire randomly during deep sleep or unconscious states, while focused thought temporarily reduces it, creating localized order. The cosmos follows a similar rhythm: stars burning, galaxies colliding, even the arrow of time itself. All are expressions of the universe's relentless march toward higher entropy. Yet within this chaos, pockets of complexity arise: planets, life, minds. Some theorists propose that consciousness might be a way for the universe to process information more efficiently, like a self-organizing algorithm that temporarily defies entropy's pull. It's as if the cosmos, in its quest to dissipate energy, stumbled upon a hack awareness itself. This isn't just abstract musing. Neuroscientists studying the brain's integrated information theory have found that consciousness correlates with a system's ability to generate and manage complex information flows. Remarkably, similar math describes how galaxies cluster or how quantum systems entangle. The common thread: both brains and black holes seem to obey a universal rule: information cannot be destroyed, only transformed. When a memory fades, its energy disperses into your brain's warmth. When a star collapses, its information lingers as Hawking radiation. The scale differs, but the underlying logic feels eerily consistent. What does this mean for our place in the cosmos? If consciousness is a localized expression of universal information processing, then your thoughts aren't just happening inside the universe, they're part of its ongoing computation. Ancient mystics spoke of the world as a living, thinking entity. Modern physics might be echoing that intuition in equations. Whether this perspective holds up to scrutiny, it undeniably blurs the line between observer and observed, suggesting that the universe doesn't just contain information, it might be information, with minds like ours as its fleeting, self-aware nodes. From the firing of a single neuron to the spin of a quasar, the same cosmic code could be running, whispering that reality is less a thing than a process, an endless dance of data unfolding in the dark. Watch an ant colony at work, and you'll witness a marvel of decentralized intelligence, thousands of tiny workers scurrying in what seems like chaos, yet collectively building intricate tunnels, foraging with military precision, and even farming fungi. No overseer directs this organized frenzy. Each ant follows simple rules based on local cues, like pheromone trails or encounters with nestmates. Now zoom out to a stellar nursery, where vast clouds of gas and dust collapse under gravity's pull, fragmenting into dense knots that ignite as newborn stars. At first glance, ants and star formation couldn't seem more different, one a biological collective, the other an astrophysical process. Yet dig deeper, and you'll find the same underlying principle: complexity born not from top-down control, but from countless tiny interactions following nature's rulebook. The magic lies in emergent behavior. An ant doesn't grasp the colony's grand design. It merely responds to chemical signals left by others, reinforcing busy trails or abandoning dead ends. This creates a feedback loop where efficient pathways amplify while inefficient ones fade. Star-forming clouds operate similarly. Individual gas particles don't know they're part of a collapsing nebula. They simply obey gravity and collide with neighbors. Yet these micro-interactions, multiplied across light years, create regions of escalating density. Like ants concentrating on a food source, gas clumps where gravity's pull is strongest, until the pressure triggers nuclear fusion. Both systems transform simplicity into sophistication, proving that complexity doesn't require a conductor, just rules, repetition, and time. The parallels extend to structure. Ant colonies exhibit fractal patterns, with tunnels branching in mathematically predictable ways to optimize airflow and resource distribution. Star-forming regions, too, arrange themselves hierarchically. Giant molecular clouds fragment into smaller clumps, each spawning stellar siblings. Even their life cycles mirror each other. When a colony grows too large, it splits via swarming, with a queen leading workers to a new site. Similarly, a massive star's birth can shred its natal cloud, triggering cascading star formation nearby. Both systems balance growth and dispersal, as if evolution and astrophysics arrived at the same playbook for sustainable expansion. What makes this connection more than a neat analogy? For one, it reveals a universal strategy for building order. Scientists model ant behavior using agent-based simulations programs where simple algorithms generate complex outcomes. Astronomers use nearly identical math to simulate star formation, tweaking variables like turbulence and gravity. The overlap suggests that nature recycles optimization strategies across scales. An ant's pheromone trail and a gas filament light years long might both be expressions of a deeper logic. Systems self-organize when information flows locally but impacts globally. This kinship isn't just academic, it's reshaping fields from robotics to urban planning. Engineers design swarm robots that mimic ant colonies to explore disaster zones, while astrophysicists borrow their algorithms to model how galaxy clusters evolve. Even blockchain technology echoes these decentralized principles, with nodes reaching consensus without central authority. The lesson: whether you're designing a smart city or probing stellar nurseries, the universe keeps pointing to the same truth. Grand designs can emerge from humble rules, and complexity thrives when control is distributed. So the next time you see ants marching in line or a Hubble image of a star-studded nebula, remember, you're witnessing the same cosmic algorithm at work. One unfolds in the dirt beneath your feet, the other in the depths of space, yet both whisper that the universe's most breathtaking order arises not from blueprints, but from the relentless, beautiful grind of small things following simple steps. Imagine a single electron suspended in a perfect vacuum, its quantum state shimmering with infinite possibilities, spinning both clockwise and counterclockwise simultaneously in a delicate superposition. Now introduce a single photon, the faintest whisper of light, and watch as that fragile quantum dance collapses into a single, definite state. This moment, called quantum decoherence, isn't just a laboratory curiosity. It's a fundamental limit on how much of reality we can perceive, eerily mirrored by the cosmic horizon that bounds our observable universe. Both act as information filters, one governing the quantum realm, the other sculpting the cosmos, yet they share a profound kinship. Where measurement ends, reality as we know it begins. Quantum decoherence unfolds when a particle's wave function, the mathematical description of its probabilistic states, gets tangled with its environment. Think of it like a spinning coin settling onto heads or tails the moment air molecules buffet its surface. In isolation, quantum systems can remain in superposition indefinitely, as experiments with ultra-cold atoms prove. But the instant they interact with the outside world, whether a stray photon, a magnetic field, or even a curious scientist's detector, their multiple possibilities decohere into a single observable outcome. This isn't just a quirk of quantum mechanics, it's the reason reality appears solid and deterministic at human scales. Decoherence sculpts the fuzzy quantum world into the sharp edges of classical physics, acting as a veil between the possible and the actual. Now leap across scales to the cosmic horizon, the farthest distance light could have traveled since the Big Bang, roughly 46 billion light-years away. Beyond this boundary, galaxies recede faster than light can reach us, their signals forever lost to cosmic expansion. Like decoherence, this horizon isn't a physical barrier but an informational one. Just as a quantum system's environment measures it into definiteness, the universe's expansion measures what we can observe, hiding everything beyond like a curtain drawn across the stage of spacetime. Both phenomena enforce a kind of cosmic censorship. Decoherence limits how much quantum reality we can witness, while the horizon limits how much of the universe we can see. The parallels deepen when you examine their mathematical roots. Decoherence arises from entanglement, the quantum links between a system and its environment that scrambles superposition into classical certainty. The cosmic horizon, similarly, emerges from relativity's equations where space-time stretching severs causal connections. both processes hinge on entropy, a measure of disorder. In decoherence, entropy quantifies how much information leaks into the environment. At the horizon, it defines the maximum information content of a spacetime region, as proposed by the holographic principle. It's as if the universe applies the same logic to quantum states and galactic surveys. Beyond certain thresholds, information isn't destroyed but rendered inaccessible, like pages torn from a cosmic ledger. What makes this connection more than poetic symmetry? For one, it hints that quantum mechanics and cosmology might be two expressions of a deeper informational physics. Some theorists speculate that the universe's horizon could act like a giant decoherence machine, with spacetime's expansion measuring quantum fluctuations into classical density variations, the seeds of galaxies. Others propose that dark energy, the mysterious force accelerating cosmic expansion, might share mathematical kinship with the vacuum fluctuations that trigger decoherence in labs. While speculative, these ideas suggest that the boundaries of observation, whether in a quantum experiment or a telescope's view, aren't arbitrary, but fundamental to how reality constructs itself. The implications ripple across science. Quantum computers battle decoherence by shielding qubits from environmental noise, much as astronomers push observational limits with gravitational waves and neutrino detectors. Both endeavors are, at heart, quests to peer behind nature's veils. Even philosophically, the parallel challenges our intuition. If reality changes based on what we can measure, does the universe out there truly exist independently of observation? From the quantum foam to the cosmic horizon, the message is clear. The cosmos loves hiding its secrets, not out of spite, but because the act of revelation is woven into the fabric of existence itself. Picture a honeybee darting between wildflowers, its fuzzy legs dusted with golden pollen as it unknowingly ferries life from bloom to bloom. This delicate dance of pollination weaves an invisible web of genetic exchange, allowing plants to adapt, diversify, and thrive. Now pull back, way back, until entire galaxies fill your view, each a swirling metropolis of stars. When these cosmic giants collide, they don't just crash and destroy, they engage in their own breathtaking transfer of material, trading stars like pollen grains across the void. At first glance, the scales couldn't be more different. A bee's wingspan versus a galaxy's 100,000 light-year embrace, yet both processes are engines of evolution, stitching diversity into the fabric of their respective worlds through the quiet art of exchange. Consider how a single bee visit can alter a flower's destiny. As pollen grains hitch a ride to neighboring plants, they shuffle genetic decks, creating hybrids that might resist drought, attract new pollinators, or bloom in richer colors. Over millennia, this relentless barter builds ecosystems resilient to change. Galactic mergers operate on the same principle, just with starlight instead of nectar. When galaxies like our Milky Way and Andromeda eventually collide, their gravitational tango won't be a destructive smash but a slow, graceful pirouette lasting billions of years. Stars too distant to physically collide will be flung into new orbits while clouds of gas and dust mingle, igniting bursts of stellar birth. Like pollen mixing between isolated fields, stars from one galaxy become citizens of another, carrying the chemical signatures of their birthplaces into fresh cosmic soil. The mechanics of these exchanges reveal even deeper parallels. Bees follow floral flight paths, routes optimized for energy efficiency, often guided by ultraviolet patterns invisible to human eyes. Similarly, galaxies don't merge randomly. They follow the filamentary highways of the cosmic web, drawn together by dark matter's gravitational topography. A bee navigates using polarized light and scent gradients, Galaxies navigate by the curvature of spacetime itself. Both systems rely on invisible scaffolds to guide their collisions, ensuring exchanges happen where they'll have maximum impact. Even the timescales, though vastly different, mirror each other proportionally. A bee's pollination season is to a flower's life cycle what a galactic merger is to the universe's lifespan, a fleeting yet transformative encounter. What's truly astonishing is how both processes turn chaos into creativity. A beehive's chaotic foraging yields precise genetic outcomes, just as the violent turbulence of colliding galaxies spawns precisely structured spiral arms. Take the tadpole galaxy, its tail stretching across space like a smear of cosmic pollen, a direct result of a smaller galaxy plowing through its disk, scattering stars in a wake of stellar seeds. On Earth, orchids trick bees with elaborate deceptions, luring them into pollination without offering nectar. In space, galaxies like the antennae pair use tidal forces, gravity's version of floral deception, to strip gas and stars from one another. Evolution, whether biological or galactic, thrives on these strategic exchanges, where what appears random is anything but. The consequences ripple across time. Just as pollinator-dependent plants dominate Earth's ecosystems, merger-shaped galaxies dominate our cosmic neighborhood. Over 80% of large galaxies show scars of past collisions, their shapes distorted, their star populations mixed. Without these mergers, galaxies would remain small, isolated, and chemically stagnant. Much like flowers that never cross-pollinate would languish in genetic poverty. Even life's building blocks might depend on this cosmic commerce. The gold in your jewelry was likely forged in neutron star collisions during galactic mergers, then scattered across space to eventually seed planets like ours. This connection isn't just poetic, it's a lesson in interdependence. Conservationists fret over pollinator decline because ecosystems unravel when exchanges falter. Astronomers, similarly, study galactic mergers to understand how the universe redistributes the heavy elements essential for planets and life. Both systems whisper the same truth: isolation breeds stagnation, while collision, whether between bee and blossom or spiral and elliptical, fuels innovation. From the micro to the macro, evolution's most vibrant chapters are written not in solitude, but in the electric moments when worlds brush against one another, trading pieces of themselves to weave a richer, more resilient whole. Deep inside every cell in your body, a microscopic ballet unfolds, long chains of amino acids twisting and turning, searching for the perfect shape to perform their biological roles. This intricate dance, known as protein folding, is one of nature's most elegant optimization problems. A protein might have more possible configurations than there are atoms in the universe, yet within milliseconds it collapses into a single, precise structure. The secret: energy minimization, the protein naturally settling into the state requiring the least energy, like a ball rolling downhill to find the valley's lowest point. Now shift your gaze to the cosmic scale, where stars and galaxies warp the fabric of spacetime itself, creating gravitational wells that planets and light naturally follow. At first glance, a protein's folds and spacetime's curves seem unrelated until you realize both are playing by the same fundamental rulebook, where nature relentlessly seeks the most efficient path. Take hemoglobin, the protein that carries oxygen in your blood. Its complex, knotted shape isn't random. It's the exact configuration where electromagnetic forces between atoms balance perfectly, creating pockets perfectly sized to grip oxygen molecules. The folding process is so precise that even a single misplaced amino acid can lead to diseases like sickle cell anemia. Similarly, Einstein's equations reveal that spacetime doesn't curve arbitrarily around a planet or star. It warps in the most efficient way possible, minimizing what physicists call action. Just as a protein's shape emerges from the interplay of atomic forces, a black hole's gravitational field is the space-time equivalent of a perfectly folded protein, a geometry where energy is distributed optimally, leaving no wasted curvature. The parallels extend to how both systems handle imperfections. When proteins misfold, cellular machinery like chaperones step in to refold or recycle them, preventing toxic clumps. In the cosmos, spacetime reacts to irregularities too. Gravitational waves, ripples in spacetime, are the universe's way of smoothing out cosmic kinks, radiating away excess energy when massive objects like neutron stars collide. Both processes reveal a self-correcting tendency, as if nature abhors inefficiency at every scale. Even the mathematics echo each other. The energy landscapes biologists used to model protein folding resemble the geodesic equations describing particle paths in curved spacetime. It's as if the universe speaks a unified language of optimization, whether navigating the contours of a protein or the slopes of a gravity well. What makes this connection more than poetic symmetry? For one, it suggests that energy minimization might be a universal principle governing everything from quantum interactions to galactic clusters. Some biophysicists even borrow tools from general relativity to predict protein folding pathways, treating amino acids like masses warping an abstract folding landscape. Conversely, theories like loop quantum gravity explore whether spacetime itself might emerge from discrete, protein-like building blocks at the Planck scale. This crossover isn't just analogy, it's a hint that biology and cosmology might be two expressions of a deeper computational process, where reality constantly calculates the most efficient configuration for any given set of constraints. The implications ripple across science. Understanding protein folding could unlock cures for Alzheimer's or Parkinson's, where misfolded proteins run amok. Meanwhile, decoding spacetime's curvature helps us map dark matter or harness gravitational waves. But perhaps the most profound insight is philosophical. Whether sculpting a molecule or the cosmos, nature appears obsessed with elegance, wasting nothing and always seeking the simplest path. From the helix of a protein to the spiral of a galaxy, the universe whispers that beauty and efficiency are inseparable, and that the same cosmic rules shape the very small and the unimaginably large. Stand on the crest of a windswept dune in the Sahara, and you'll witness nature's artistry in motion, rippling waves of sand frozen mid-flow, their curves echoing the swells of a petrified ocean. These shapes aren't random, they're the signature of fluid dynamics, the invisible hand of wind sculpting grains into mathematical perfection. Now leap from Earth's deserts to the rubble-strewn surface of an asteroid like Bennu or Ryugu, where NASA spacecraft have captured eerily similar patterns, undulating landscapes of pebbles and dust arranged in dunes and ridges, as if an unseen breeze had combed them into place. The catch: asteroids have no atmosphere, no wind to shape their terrain. Yet here they are, mirroring Earth's dunes with uncanny precision, revealing a universal language of granular flow that transcends environment's gravity and even the presence of air. The secret lies in how particles behave when they're nudged into motion. On Earth, wind skims loose sand grains, launching them in short hops called saltation. Each bouncing grain dislodges others, creating a cascading ripple effect that builds dunes over time. Asteroids achieve similar patterning through a far stranger mechanism: thermal fracturing. As these space rocks spin, their surfaces bake in sunlight, then freeze in shadow, a daily cycle that stresses boulders until they crack into fragments. The resulting debris behaves like a fluid, sliding and settling into low-energy configurations, just like sand grains finding the steepest slope they can hold without collapsing. In both cases, whether pushed by wind or microgravity, particles obey the same fundamental rule: seek stability, minimize energy, and let physics do the sculpting. The parallels run deeper than mere appearance. Earth's dunes migrate downwind, their shapes evolving as grains avalanche down the slip face. Asteroid surfaces, too, exhibit slow but measurable movement. NASA's OSIRIS-REx mission watched as Bennu's particles rearranged themselves over months, almost like a desert shifting under an impossibly faint breeze. Even the scales align proportionally. A terrestrial dune might stretch hundreds of meters, while an asteroid's microdunes span mere centimeters, yet both adhere to the same geometric ratios, their steepness dictated by the angle of repose, the steepest slope a granular material can maintain before sliding. It's as if the universe distilled dune physics into its purest form, then applied it indiscriminately, whether to Sahara sands or asteroid regolith. This connection isn't just a visual quirk, it's reshaping planetary science. By studying Earth's dunes, researchers can predict how asteroid surfaces might behave during spacecraft landings or sample collection. The Hayabusa 2 mission to Ryugu, for example, faced unexpected challenges when its touchdown stirred up boulder fields that flowed like liquid, a phenomenon familiar to geologists studying sand avalanches. Conversely, asteroid observations are refining our understanding of granular physics here on Earth, helping engineers design better systems for handling powders in industries from pharmaceuticals to construction. The cross-pollination of ideas reveals a profound truth. The laws governing particles are universal, whether they're sand grains dancing on a breeze or asteroid fragments jostling in the gentle tug of microgravity. Perhaps most poetic is how these patterns blur the line between solid and fluid. Dunes and asteroid terrain exist in a curious in-between state, technically solid, yet flowing over time like thick honey. This duality hints at a deeper principle, that matter, under the right conditions, forgets its categorical boundaries and behaves simply as energy seeks equilibrium. From the deserts of Earth to the rubble piles of the asteroid belt, the cosmos keeps whispering that form follows function, and that the same elegant physics weaves the tapestry of landscapes across every conceivable environment. The next time you see a windswept dune, remember, you're looking at a close cousin to the alien hills of Bennu, both shaped by the universe's relentless drive to turn chaos into order, one grain at a time. Listen closely to your own heartbeat, not the steady drumming you might expect, but the subtle, ever-changing gaps between each pulse. This phenomenon, called heart rate variability, isn't a sign of imperfection but a testament to your body's exquisite sensitivity, constantly adjusting to stress, breath, and even emotion. Now train a radio telescope on a pulsar, the dense, spinning corpse of a dead star, and you'll detect a similar rhythm, flashes of radiation so precise they rival atomic clocks, yet occasionally stuttering with minute delays or jumps. At first glance, a human heartbeat and a cosmic lighthouse seem worlds apart, but their shared irregularities reveal a profound truth: complex systems, whether biological or astrophysical, dance to rhythms far richer than simple metronomes. Your heart's variability stems from a delicate tug of war between your sympathetic and parasympathetic nervous systems. One revs you up for action, the other slows you down to rest, their interplay creating a dynamic, living rhythm. Athletes often exhibit high variability, a sign of cardiovascular resilience, while chronic stress can flatten these natural fluctuations. Pulsars, too, experience their own version of stress. These neutron stars, some spinning hundreds of times per second, are paragons of stability, their rotations predictable down to microseconds over decades. Yet occasionally they glitch, suddenly speeding up by a fraction or experience timing noise, tiny deviations caused by starquakes, magnetic field shifts, or even the drag of interstellar plasma. Like a heart adapting to a sudden sprint, a pulsar's rhythm reflects its environment and internal dynamics. The parallels extend beyond mere analogy. Mathematically, both systems exhibit fractal-like patterns in their timing variations, fluctuations that repeat at different scales, whether you're analyzing minutes of heartbeats or years of pulsar data. Cardiologists use tools like detrended fluctuation analysis to quantify this complexity, while astrophysicists employ nearly identical methods to classify pulsar timing noise. It's as if nature encodes complexity with the same mathematical brushstrokes, whether painting the rhythms of life or the spin of stellar remnants. Even their silences echo each other, just as a flatlined heart signals crisis. A pulsar's sudden radio silence, like the enigmatic pulsar deathline, hints at magnetic field decay or other terminal transitions. What makes this kinship more than coincidence? For one, it underscores how feedback loops govern stability across scales. Your heart's variability arises from continuous negotiation between brain, hormones, and muscle, a biological feedback system fine-tuned by evolution. Pulsars, too, are embedded in feedback webs. Their crusts adjust to internal superfluid vortices, while external torques from debris disks or companion stars tweak their spin. Both systems balance predictability with adaptability, proving that resilience isn't about rigidity but responsive flexibility. The implications ripple across disciplines. Space agencies monitor astronauts' heart rate variability to assess stress in microgravity, while pulsar timing arrays networks of observed neutron stars serve as galactic-scale detectors for gravitational waves. Some researchers even speculate that advanced civilizations might use pulsars as navigation beacons, mirroring how our own autonomic nervous system steers us through life's challenges. Whether in the human chest or the cosmic deep, variability isn't noise, it's the signature of a system alive with interaction, whispering that the most reliable rhythms are those brave enough to bend. Consider the sentence you're reading right now, a cascade of words arranged in clauses that nest inside one another like linguistic matryoshka dolls. This recursive structure, where phrases embed within larger phrases, is the hallmark of human grammar, allowing us to build infinite complexity from finite rules. Now shift your gaze to the night sky, where swirling galaxies mirror the structure of their spiral arms, and atoms echo the orbital dances of planets. The resemblance isn't just aesthetic. Some physicists and linguists propose that reality itself might operate on a kind of cosmic syntax, with the universe constructing its grandeur through recursive, self-similar laws as precise as any grammatical rulebook. Take the Fibonacci sequence, a mathematical pattern where each term is the sum of the two before it. This recursion appears in sunflower seeds, hurricanes, and spiral galaxies, nature's way of building complexity through repetition with variation. Human language does the same. A simple sentence like, "She thinks that he knows they left," embeds clauses within clauses, creating depth through grammatical recursion. Strikingly, the same pattern governs quantum mechanics, where particles exist in superpositions of states until measured into definiteness, a kind of syntactic collapse from possibility to actuality, mirroring how ambiguous phrases resolve into clear meaning when parsed by the brain. Parallels grow even more compelling when you examine generative grammar, the linguistic theory that all human languages share an underlying rule set. Just as grammar generates endless valid sentences from finite components, the universe's fundamental laws, like the standard model of particle physics, generate endless structures from a handful of particles and forces. Both systems are productive. English can craft a novel sentence never before spoken, just as physics can arrange quarks into atoms never before formed. Some theorists, like physicist David Bohm, speculated that reality might literally be a kind of language, with quantum events as its words and space-time as its unfolding narrative. This idea isn't mere metaphor. In quantum field theory, particles emerge as excitations in underlying fields analogous to how words emerge from the fields of phonemes and morphemes in linguistics. The Higgs field, for instance, assigns mass to particles much like adjectives modify nouns, adding specific qualities to base terms. Even entropy, the measure of disorder, behaves like a syntactic constraint. Just as garbled word order scrambles meaning, high-entropy systems lose coherent structure. The universe, it seems, might be less like a machine and more like a cosmic sentence, with its laws as the grammar and its phenomena as the ever-unfolding clauses. What makes this connection more than poetic analogy? For one, it reshapes how we view scientific discovery. Deciphering the universe's grammar could mean uncovering deeper symmetries, the equivalent of finding all languages share a universal grammar. String theory, with its vibrational notes composing reality, even borrows terminology from music and linguistics. Meanwhile, computer scientists use generative grammars to simulate cosmic structure formation, proving that recursive rules can indeed build fractal universes in silico. The implications ripple beyond academia. If reality operates syntactically, then consciousness, our internal parser, might be uniquely tuned to decode it, explaining why mathematics, the universe's syntax, feels unnervingly effective at describing nature. Ancient mystics spoke of the logos, a generative word underpinning creation. Modern physics might be rediscovering that intuition in equations. From the recursive depths of a sentence to the self-similar vastness of cosmic webs, the universe keeps whispering that order emerges not from chaos, but from rules, a syntax as elegant as sonnets, as boundless as stars. From quantum foam to galactic superclusters, these 32 cosmic connections paint a portrait of a universe that refuses to be neatly divided. What we once saw as separate realms, the microscopic and the cosmic, now reveal themselves as chapters in a single, unfolding story, written in the language of fractal geometry, harmonic resonance, and emergent patterns. The golden ratio that shapes a seashell spiral doesn't just stop at the shoreline. It echoes in the whirlpool arms of distant galaxies. The same magnetic reconnection that powers solar flares crackles in laboratory plasmas no larger than your palm. Even the neurons firing in your brain as you process these words mirror the cosmic web's filamentary structure, as if the universe sketched its grand designs with the same brushstrokes at every scale. This isn't mere coincidence, it's a clue to reality's deepest nature. The universe operates not as a collection of isolated phenomena, but as a symphony of interwoven processes, where the behavior of quarks influences the fate of galaxy clusters, and the logic of ant colonies mirrors the growth of stellar nurseries. Physics, biology, and mathematics converge on a startling truth. Complexity arises from simplicity when the same rules are allowed to play out across dimensions and epochs. The quantum fluctuations that birthed galaxies are kin to the randomness that shapes a murmuration of starlings, both governed by the elegant mathematics of emergence. What does this mean for us, the conscious observers perched between these scales? It invites a radical shift in perspective. We're not just inhabitants of the cosmos, we're its awake, self-reflective expression, Stardust, that has learned to trace its own origins. The carbon in our cells was forged in dying stars. The rhythms of our hearts echo pulsars' precision, and the very thoughts we form may ripple with the same informational logic that structures black holes and bee colonies alike. This interconnectedness isn't poetic metaphor but scientific revelation, a reminder that the boundary between us and the universe is far thinner than we ever imagined. So as we close this journey, consider how these mirrors change your gaze. When you next see a snowflake, will you picture the crystalline crust of a neutron star? When you hear of entangled particles, will you wonder if galaxies too are linked by some unseen thread? The cosmos has handed us a Rosetta Stone, decoding its whispers from the infinitesimal to the infinite. Now it's your turn to listen and to marvel. Drop a comment below about which connection reshaped your view of reality, and hit subscribe to keep unraveling the mysteries that bind the quantum to the cosmic. The universe's greatest lesson: we're all part of the same pattern, forever unfolding.